Well, let's discuss Kepler's laws. I'm putting this on a separate video because the other one was right at about 10 minutes already. So, law number 1, the law of ellipses, that planets follow elliptical paths with the sun at one focus. So we have the planet, the two foci, and if we connect a line from each focus to the planet and add those lengths together, we get the average radius, a plus b over 2. It's a constant value as you go around. You might have seen me or somebody else in the past have a string that connects these together. You take a pencil and you can trace out the actual ellipse around these foci. All right, so these two values are constant if you add them together and divide by 2. So that's the average radius. All right, so that's about it for law 1. Law number 2, take us a little longer. We have the sun, the planet, and let's draw a radius line from the sun to the planet, and that planet is going to sweep along this, move along this curved path. So later on in some delta t, it finds itself over here. And it has this line connecting the sun and the planet has swept out across an angle d theta, which of course is a differential. So S is equal to rd theta. That's the arc length. Now, the motion of the planet is along the trajectory. Notice that v is not perpendicular to the radius itself. The perpendicular velocity is a fairly important quantity, so let's consider that. So we have angle phi between these two here. And the actual perpendicular part of the speed is v sine of phi. Now, that speed, as we've learned in the past, in terms of angular velocity, the angular velocity corresponds to v by dividing by r. Or we can say v perpendicular is r omega. But omega is d theta dt. So it's r d theta dt, or r omega. Now the differential area here, represented by what will be a very, well, differentially thin triangle here. All right, so that this line and this line, leg, radii particularly, are the same effective length in the differential. So it's 1/2 r times s, and that's 1/2 r. S is r d theta, so there we go. And that's 1/2 r squared d theta. Well, the rate at which that area is swept out, so not just the area itself, but the rate at which the area is produced, is called the sector velocity. All right, and that's an important quantity for orbital considerations. What is that sector velocity? Well, just divide by dt. So we have 1/2 r squared d theta dt, or 1/2 r squared omega, right? Now that's also 1/2 r times r d theta dt, and d theta dt times r is v sine of phi again. So the sector velocity is 1/2 rv sine of phi. Now that 1/2 rv sine of phi should remind you of something, namely a cross product, 1/2 r cross v. So we have a cross product of the radius and velocity vectors. I'm going to play a little trick here now. I'm going to divide by m. So we have 1 over 2m times r cross mv. That's legal, isn't it? And you'll notice what r cross mv is. Now, I have a reason for doing this. Trust me. Maybe not very good reason, but nevertheless a reason. So that's 1 over 2m times r cross rho. Linear or translational momentum. So dA dt sector velocity is, well, what's r cross rho? Oh, that's right. It's angular momentum. There you go. So the sector velocity is angular momentum over 2m. Well, m is constant, of course, and so is 2. And, oh, angular momentum is conserved, so angular momentum is constant. This whole thing, namely the sector velocity, the rate at which the angle is swept out by a line joining the sun and the planet, is a constant. Very interesting. So here we have the planet, and in delta t, That line connecting the sun to the planet sweeps out area A1 at a different place in the orbit, say over here. It sweeps out A2 in the same amount of time delta t. Those pi slices are the same. Since dA dt is a constant, it follows then that A1 is equal to A2 in time delta t. All right, now we have made a pretty bold assumption here, haven't we? The angular momentum is constant, as I said. Well, is it really? Let's just make sure that we agree that, in fact, the angular momentum is constant. Now, in terms of angular momentum being conserved, you might just have a little bit of skepticism in that when you consider that the sun is pulling on the planet, you're saying, well, there's a part of it that's speeding up the planet, and the planet speeds up, isn't its angular momentum changing? Well, you'll also notice something else here. Look at the direction directly toward the sun that is pulling on it. Oh, so what we're really concerned about here, we got the radius and the force, is the rate at which angular momentum is changing, but the rate at which angular momentum changes is the definition of torque. So is there any torque? And now when you look at the direction of this force, you realize that the line of action goes right through the sun, which is considered essentially the axis of rotation, if you will. So torque is R cross F, and the radius and the force is along the line of action, so it's the same line as the radius. So RF sine of theta equals 0. And what we've just done is establish that the angular momentum is indeed constant. Thus, angular momentum, R cross rho, which is mv r perpendicular, or we could express this as mv perpendicular r, and that is constant. Thus, A1 is equal to A2 in delta t, which is also equal to A3, A4, A5, etc. There is no torque, therefore no change in angular momentum. How about the mechanical energy? All right, well, mechanical energy is K plus U, 1/2 mv squared minus gmm over r. Now, consider, let's see, when we speed, that we're speeding up as we go along here. We're speeding up. Oh, greater kinetic energy. That must mean the potential energy is less. Well, it's closer, so it should be less. When we're out here, the potential energy is greater, further away from the sun, which means the kinetic energy would have to be less. And in fact, it is. It's moving slower out here and then speeds up as it goes around the sun and then slows down again. So this whole thing is constant as the energies transition between kinetic and potential. Now, the shapes of the orbit. If the total mechanical energy is 0, the orbit is parabolic and the mass can escape. Now, the parabola is a unique, a very special mathematical solution. The mass will escape, but it will take infinite time to get infinite distance, and in that infinite time, it'll come to a stop. Any more energy than that, and we have a positive mechanical energy, in which case the orbit is hyperbolic, and there's an unlimited number of solutions for that. Anything more than 0, the mass escapes. If the total mechanical energy is negative, then the orbit is elliptical, and these are the most common, probably the most interesting, because if they're hyperbolic or parabolic, then it's kind of a one-shot. Passes an object like sometimes a comet might pass by the sun in a hyperbolic orbit, and away it goes, never to return. If it's elliptical, it's bound by gravity to the large central mass. And finally, let's consider Kepler's third law, which is going to relate the radius of orbits around a large central body and the period of that orbit. Now, even though this is Kepler's law, I'm going to throw in Newton. I'm going to mix Newton and Kepler together here because Newton really described the mechanism. So let's actually start with Newton, where he said the force of gravity is equal to the centripetal force, which keeps that satellite moving in an orbit around the Earth, or the large central mass. So Fg is gmm over r squared is mv squared over r. Also, m4 pi squared r over t squared. There's a whole lot you can do with these three equations. You can solve for any of the variables in terms of the other part of the equation. So, for instance, v is square root of gm over r squared when you relate this one and this one. How about if we relate this gravitational tug and this centripetal force, solve for the period, and we get that. So there's a whole lot of different things we can solve for. We can solve for the mass of the large central body. It's the second time we're doing that. There it is. And what you see here in this mass now is an r cubed over t squared. Now this r cubed over t squared is what Kepler discovered to be a constant for any object orbiting a large central mass. So this satellite will have that. The moon around the Earth will have that same r cubed over t squared. Actually, he was doing it for the planets around the sun, so all the planets have the same r cubed over t squared. So what is r cubed over t squared? Well, it's gm over 4 pi squared. So this is Kepler's constant, and it's really Newton's form, which is this gm over 4 pi squared is the actual value of the constant. Notice that the constant is going to change based on the mass of the large central object. So that's law 3. True for that, true in general, but in particular, the value of that constant is related to the large central mass, proportional to it. And that is a basic introduction to Kepler's 3 laws.